Okay, last lecture we stopped at example 8. So we stopped at impact. So impact have a straight line impact and oblique impact like this one. Okay, today we go into angular momentum. So the word angular means we need to use the R and D. The word momentum still the same, but in this case, because it's angular momentum, actually angular momentum you accept. Sorry. What is momentum? MV. Momentum is MV. Then you add the word moment of momentum. What is moment? You take the vector, multiply by the perpendicular distance. Then you create moment. Okay. So this one angular momentum actually is MOM, a moment of momentum. So if you look at this one, you have an object dot here with a momentum m multiply velocity. You get a momentum. Okay. Then you take the momentum line multiply by the perpendicular distance d, you get the angular momentum. We will use capital H as the angular momentum. And the positive direction is using right hand rule. Okay, using right hand rule. So today we learn MOM, moment of momentum. Means we take the momentum, multiply by a perpendicular distance, we get moment of that momentum. Okay. They use capital H. So scalar one is we use M, we multiply D, we get the momentum, moment of momentum. So you extend this line, right? So D cross to M, D cross to M, F cross to D. So this one, if you refer to this diagram, positive direction will be, if you take the D and the momentum, it will be anti-clockwise. So anti-clockwise, you look at your right hand rule. So if this one is anti-clockwise, you look at the thumb, it's the axis of the moment. Okay, this one, if you understand how to get the moment of momentum, you just take momentum mv multiplied by the perpendicular distance d, you get the MOM or angular momentum. If you have two, if we have a, okay. So there are two ways of solving. Either you use scalar approach or you use vector approach. So if the question is in three-dimensional, you're forced to use vector formula. You are using same concept also. We use R cross MV. Okay. R cross to MV is R cross to MV. And your thumb is pointing this way, pointing this way. And the blue circle is the momentum. Your thumb is the axis of the momentum. Okay. R cross MV. So when you have cross product, you can use matrix form. Okay, you can turn into metric form. We can write this R cross MV by metric form. What is the R? R is this one. So you can write IJK and then RF, RY, RZ. And then your MV in X direction, MV in Y direction, MV in Z direction. The rest is multiplication product of matrix. So if you want to find I, you cross I, take J multiply K minus RZ multiply MV. All right. Previously, we have learned how to do cross product already. I hope you remember this circle. Okay. So I multiply J, you get positive K if you do anti-clockwise direction. If you do clockwise direction, you get negative sign. Okay, this will be the diagram for the cross product. This one is the cross product. Okay. So this one, I cross I, 0. Dot product, I dot I, you get 1. I dot j get 0. So there's a difference between dot and cross. So don't mix between them. Okay, so if you understand this concept, angular momentum or moment of momentum equal to h equal to r cross mv. This one, you use the cross when you see three-dimensional problems, where you can derive the direction in x, y, z or in I, J, K, then you put in this form. Then you do the matrix solution. This is a further derivation from the equation of motion. F equal to ma, A equal to beta. Even mass and velocity, you still can do mass and velocity or acceleration. Okay. If you're given velocity in equation, you differentiate it, you get acceleration. You still get back the 4. Okay. So you take this, all the F equal to ma, put inside here. R cross mv dot. So how to do the cross products of this one? So you write as okay. So you know that hold on. Okay. Okay, I should use capital H. I should use capital H, but you use M also correct lah, because it's moment. So this M actually is H, but you write M is also correct lah, because it's a moment. So you write capital H just to differentiate this one from the ordinary moment. So H dot means you take this equation, you time differential with the T. Okay, time differential with the T. Hold on. H equal to okay. H equal to V moment of O, moment equal to R multiplied by F, right? This one multiplied by moment. Okay, the slide actually want to link what is the moment and the H. So you derive from V dot is MA, from F equal to MA. And then this one actually, later you link back the result here back to here. So this one is just from the H, just now without H without the dot. H is R cross MV. Okay, H equal to R cross MV. And you want to derive time differential, you put a dot there. Put a dot there, then it's a time differential between R cross MV. So R cross MV, this is the chain reaction or chain products. How to do this one? You refer to appendix B. How to do this one? You arrive at this one. So you when you do chain products, you differentiate this one, then you maintain this one, you'll get this one. You differentiate this one, maintain this one, get this one. Maintain this one, differentiate this one, you'll get this one. Okay, so these are the side note. These are the side note. Okay. M dot M cross MV. Okay. This one I don't test you what let you know the derivation. At the end, the moment equal to the time differential of the angular momentum. At the end is this one. Okay. So there are two important equation. Is this one. If you want to calculate moment in the three-dimensional as a result of force, you can use time differential of your angular momentum. Okay. So the left-hand side is a resultant of moment about O, result from the forces. Left-hand side is because of the forces. Forces multiplied by the R or cross R, you get moment. On the right-hand side is because of the angular momentum. Right-hand side is because the effect of momentum, MV. Okay, so MV multiplied by the R, you get the moment. So this equation, you're actually combining the effect of force equal to the effect of momentum. Okay, so this one will link you up with the F effect and the momentum effect. You link the force and the velocity, how they come together by using this equation. Okay. At the moment, just accept this one. We'll back to this one when we look at chapter outside particles, rigid body. Okay, rigid body. Okay, so basically, what we learned today is all the moment at a certain point, in this case O, will equal to sum of, we can write sum of H dot lah, if you want, or H dot. So you see how the question can be asked you. So this one, when you see the question come with the R and theta, is fall under angular momentum. When you see the question with the circular sliding or flat, but the question give you O and R and theta with the velocity, is actually hint you need to use this equation. Moment equal to the H dot. H dot means time differential of your angular momentum. Okay. So you're having a box showed in a mass, have a mass travel on a smooth circular ramp. So smooth, when you have a smooth, you have a normal force, but you don't have a friction. Such as this one angle typo error, angle theta, not U, at a speed of V, determine the angular momentum about point O. Angular momentum is moment of momentum, mv multiply R. At this instant, the rate of increase in the speed, this one is acceleration actually. Rate of increase in speed, it means acceleration in tangent direction. So this is a curve. So when you draw, you know where is normal and tangent. Draw free body diagram. As usual, you should, because this is a curve motion. So start from curve, you should draw tangent and normal. Okay. By now, you should already know where is tangent, where is normal already. Then you are given M. So given M means it asks you to put in force. What force is W? Okay, don't substitute first. Don't write mg, write W. Write W. You can write capital W equal mg, but don't just put mg. So you draw the axis O, the R direction, the R is the R. Net weight pointing down, contact force, no friction because of smooth circular ramp. So then you derive accordingly. R sign, oops, too fast, So R sign is this one. Why we need to find this one? Because we need to find the moment later. So V is tangent to the path. So this one you should already know. When you move in the circular path, velocity always tangent to the curve. Velocity always pointing tangent to the curve. So what is H? MOM, moment of momentum. Moment of momentum means you take the D multiply momentum. So in this case, we take anti-clockwise as positive because right-hand rules. So we take R multiply by the MV in Z direction. Z direction means go outside the screen. But in this case, is go inside the screen. So this is the R. Momentum is momentum is this direction. All right, in this direction, M multiply V is in this direction. So R cross R to MV. R is perpendicular distance. Momentum. So the vector and the distance should be perpendicular to find the moment. Then you find the rate of increase in speed. You multiply the whole thing, not multiply, time differential the whole thing, because you change the V into A. So when you have dot here already, you can equal to moment at a certain point, in this case at O. In this case, anti-clockwise moment is positive. Okay. How you determine positive and negative? You use the right hands and then you look at the motion. Example, this box here, V is here, MV this direction. This is R. So you look at the way your finger curve lah. So this one is go like that one. Right? This one swing like that. So yeah, so go like that. So you're pointing in, huh? So you're positive, anti-clockwise. You put in, okay. Left hand side is the moment at point O. Left hand side is the effect of force. The effect of force. Right hand side is the effect of momentum. Yeah, remember, left hand side you only look at force effect that generate moment. Right hand side you look at momentum that generate moment. Okay, so left hand side you look at the force. There are only two force, W and N. N will go through the O. D0. Okay, how you find moment? Let's say this point O. This is F. This is D. Must be perpendicular. Moment at O will be, in this case, clockwise, will be FD. FD. Okay. So when it's pointing along the O line, your D0. So no moment. But W, you need to split this W into theta. Okay. Actually, theta is here. You are interested in this component. This component, this is W sine theta. Okay. So you can put the sign in the front or inside, doesn't matter, as long as the two vector is perpendicular to each other. So you take mg or w sine theta multiplied by the r, you get the moment because of the force effect. Right hand side, you look at the momentum. Momentum is in this direction, going down. mv multiplied by the r. Why? Because it's a curvature motion, circle. Circle, your velocity always tangent to the radius. Okay, so you have r, mv, but this one is dot. Remember to put dt in the bracket because it's a dot. Okay, then you substitute. Because r and m are constant, r and m constant, r and m constant, pull this one out, cancel both sides. Okay, then you only see g equal to sine theta. As you can see, this question, you don't need mass to solve acceleration. You don't need mass value to solve. Okay. Okay. Then when you have a equal to sine theta, a equal to g sine theta, then only you substitute. So, okay. This slide is using the angular momentum method. These are you can reach the same results by using equation of motion equation by these slides. You can use F equal to ma equation and put in the same thing. On the left hand side is force diagram. Right hand side is the kinematic diagram. You cancel the m. You get dv dt equal to g sine theta. You get the same results. Okay. So there are different ways of solving. It depends on whether the question forces you to use angular momentum method or not. So you need to able to do two methods. One is F equal to ma, and another one is using m equal to h dot. That method. Okay, there are two methods. So the next one, before this, we have principle, like you see in your test one. Previously, you have principle of work and energy. Today, you learn another principle. We call principle of angular impulse and momentum. So if you understand this one is the change of work equal to the change of energy. Energy here can be kinetic, can be potential. But normally we only look at kinetic, change of kinetic energy. Okay, so here also same. Here we look at impulse and momentum. So if you look at the derivation, moment, this one is moment, and this one is the moment of momentum, mh, h dot. This is rate of change of moment of momentum. Again, if you see this one, m and h dot, m left hand side is because of the force effect. Right hand side, h, capital H, is because of mv, momentum effect. Remember that. Okay, you rewrite in 1 over t because you want to derive the principle of this one. Again, I won't ask you how to derive. I will ask you to apply on it. You move your dt to the left hand side. When you see dt, it means you need to integrate already. You see dt, you need to integrate already. So you integrate, you arrive at h2 minus h1 on the right hand side. This one is the integration of moment multiplied by the time. Okay, then you arrange what happened before equal to after. It's the same structure as what you see in the principle of work and energy. So we see the question asks you use principle of angular impulse. This is angular impulse. This is angular impulse. M multiply T impulse always related to time. This is the angular momentum. Angular momentum. Okay. So this is called principle of angular impulse. Actually, it should be angular impulse and angular momentum, but we don't want to repeat the word angular, so we just use one time angular. Yeah. So this is important for your analysis. Okay. So you can further, sometimes you can break this M into the vector form. You know that M equal to R cross F. Uh, yes. This one. Uh, you just need to remember this one. You derive from the M equal to H dot. You derive, but I won't ask you how to derive. I will ask you straight away use this one. But use principle of angular impulse and momentum, determine something. Then we expect you to write this one. Okay, so if your answer you use other notation or other alphabet label, in our module, H represent angular momentum. Okay, let's see how we apply, how we apply. You see this one is momentum, impulse momentum. This is principle of impulse momentum. This is principle of angular impulse, angular momentum. This is linear. This is, you can say in 3-dimensional. When you're given R and theta in a question, then you use this one. Okay. If you're using just normal 2D, then you use this one. Yeah. So how to differentiate this one? This one, it depends on the question. You see lah. So the first one, principle of impulse and momentum, you can express in X, Y, Z. Okay. This one you look at X direction, all the velocity, force, and velocity, all in X. You write another set in Y, write another set in Z. You apply the same for the side. Oh, one more. Then this one. This one. Okay. So we have 4 equations. We have 4 equations. Okay. You have 2. You can split the first one, principle of linear impulse and momentum, into 3, plus one more that you learned today, principle of angular impulse and momentum. So here, this equation, they are one unknown, V1, F, and V2. There are 3 unknown here. So 3 unknown, you need 3 equation in X, Y, Z direction. This one, you have angular momentum. This one, you have moment because of the force. And this one is angular momentum. So this one is to additional one more equation, just in case anything missing here. Then you insert this one to find any missing, either missing in mv, velocity, here anything missing with the force, here also velocity after, for example. So you have a normal. This slide actually summarizes what happened in chapter 4. Then we go into conservation. Okay. Now, every time you see conservation, previously you look at conservation of energy. Conservation of energy. So what does conservation energy? All the energy before equal to energy after. You'll only learn about two energy. Kinetic energy before plus potential energy before equal to kinetic after plus potential energy after. Same with this one. So when you conserve the angular momentum, the impulse part you take out. Thing that related to time you take out. So here, you take out the moment, impulse or moment, angular impulse related to time on you take out. So angular momentum before equal to angular momentum after. Okay, so this is called conservation of angular momentum. Okay, this one, the application of this one, conservation of angular momentum, you know this one is R cross mv, R cross mv. So this one, basically, you are finding the R or the V before. This one also R after or V after. So there are four parameters here. Okay, R cross mv equal to R cross mv before after. Okay, we see how we apply, huh? So this one, if you look at this one, you can solve using F equal to ma, no problem. But if the question forces you to use what we learned today, 1.5 megagram, you need to change into kilogram. Circular road, so means there's a tangent normal that already. So tangent normal, remember to write the ANAT equation, including the rho equation, just in case the question asks you. In this case, the rho is given 100, so you don't need to calculate the rho. Just in case the question don't give you the rho, you need to calculate the rho, means the R. Okay. You are given the F equal to time differential, there's a related to time. So when your force is not constant, your A is not constant. So A is not constant, you cannot use the three motion equation. So determine the speed of the car when the time is so and so. So there are only a few equations related to time and then ask you to find speed, which is impulse, or it is the principle of impulse something related to time, or mv, momentum. So you given the initial speed, which is v1, it asks you to ignore the size, means it doesn't matter whether big or small. The effect is the weight of the car, the M. So you draw free body diagram in 3-dimensional. Although this one look like 2D, you can solve in 3D. So why we need the Z? Because you have right-hand rules, you have the vector R cross F, that one. Okay. So the radius is 100 meter, and apologize for this curve. Actually, it's a curve. Right? I just want to draw a curve. W is point down. Write capital W. Again, don't straight away write mg here. Write capital W, the weight, because sometimes you can cancel out the W directly in the equation in your solution. If you put in m, maybe you cannot see the bigger picture. Okay, W point down. Direction mv is going forward. Right? There's a contact force. In this case, it doesn't mention, ask you if the traction force of the wheel is F. Okay, traction force of the wheel is pushing it. There's a vehicle. So there's a force in the tangent direction. Okay, in the tangent direction. So in this case, you have R direction, force in the R direction. To keep the vehicle in the curve, you need FR. FR. So we apply the principle of angular impulse and momentum about z-axis. Okay, so if you do x-axis, then angular impulse created by weight, normal force, radial function, friction force will be eliminated because they parallel to the axis or pass through. Okay, so you use this one, angular impulse and momentum. Angular momentum h1 plus angular impulse m time multiply t equal to h2 angular momentum. Then you substitute accordingly, right? So in this case, we modify the equation. This is a general equation. This equation alone can solve for three-dimensional. In this case, is using your right-hand rules, which is in z direction. All right, is circling like this. Okay, go up positive. So you modify the O becomes Z, means everything in Z direction. Okay, then you expand the equation a little bit. How you find HZ1 before? What is H? H is moment of momentum. So you take momentum mv multiplied by the perpendicular distance, which is the R. So R mv before equal to after R mv. Okay. Now some of you might ask, Dr. Can I put my R behind? Can. You bracket it. Okay, you bracket it. Because this one is actually scalar method. Scalar method, we don't look at the sequence. But if you use cross, then you have to take R in the front. Then you split the moment. Moment is R multiply F. Okay, R multiply F. So FR don't have because it's parallel to the R. You only look at this F, traction force. Yeah. Now try to understand how you convert this general equation into this one. If you understand how to convert, then the rest is just substitution. Okay. You do substitution. I do the substitution for you. I do one by one. So you take R is 100 meter. Again, mass in this question is in megagram. You will see megagram in your final also, or question 2, test number 2. Purposely put there just to trick you, just in case you use 1.5 in the calculation. It should be multiply 1000 to become kilogram. So remember to change the unit SI. Velocity is 5 before it. So you have you have clear one unknown already. No unknown here. Okay. RMC2, this one also. You know the R, the radius doesn't change in the circle. In the circuit doesn't change. M still the same, 1500. You don't know the velocity. He asks you the velocity, the speed when it's 5 seconds. So you don't know the velocity after. What about the impulse? Impulse is F cross D. R is 100. F is a equation, a quadratic equation. So you just put in there, integrate with time, constant in front, T squared integrate T cubed divided by 3. Then you substitute the T2 and T1. In this case, T1 0, T2 is 5. Okay, T1 0, T2 is 5. Unless the question asks you, it give you initial travel with the speed of 5 meter per second at t equal 1 second, then this one is 1. If the question change a little bit, it give you the time for this speed, then you need to put the time 1 here. Okay, substitute, you'll find there's only one unknown. because here you don't have any unknown after you do the integration. This one also, you have one unknown. This one you already solved, this one you already solved, so only one unknown. The answer for your reference will be 9.17 meter per second after 5 seconds. Okay. Yeah, can I? Okay, we go for another one more example. Just to use principle of angular and impulse and momentum. So here you have a disc tied with the elastic rubber or a spring that can extend when there's a force or when there's a momentum. So 2 kilogram disc rests on a smooth horizontal surface, so smooth, no friction. But again, attached to an elastic cord have a stiffness K, so means it will elongate. It will elongate when it rotates. Initially unstretched. If the disc is given velocity of 1.5 meter per second, perpendicular to the cord, determine the rate at which the cord is being stretched. Rate of which the cord is being stretched means a meter per second, means the velocity of this cord, and the speed of the disc at instant of when it at 0.2 meter. This is a design question. Means you design application for your customers. Your customer give you so and so. You need to design the motor or the vehicle that create such a performance. You draw free body diagram. This one is 3-dimensional. Okay, after the disc has been launched, it will slide along the path shown. Okay, so you will slide in a circular motion because this one is stretchable. So when this one move in a speed, this one will make a circular motion. It can be either become bigger and bigger as it build out the momentum. So you are seeing the curve with the tangent and normal direction. So you put in VD1, and when you reach a certain distance, right? So let's say we reach D position number 2. So D2 actually is a tangent direction. Then you can split into 2 directions. One is in R, another one is in another direction, perpendicular to that. Okay. Original is 5. You want to find the final location where it's at point 2. So you put in this one. So since you are taking degree level, we expect you to able to predict what happened after a certain motion. Okay, you should able to have the ability to predict what happened. Okay, so this is the skill set that we expect when you graduate with the degree program, especially engineering degree program. So you should able to see before and after. Okay, so yeah, so if unable to see means you need to work a little bit hard because this one is what we expect from your learnings in the class. Okay, so you should able to see before and after. Okay, then this is just a free body diagram. Just for the show of free body diagram to solve m dot to solve this principle of angular impulse and momentum later. Okay, so there's a contact force, there's a FC pulling inside, means the cord, the force pulled by the force. You imagine you are that object of this. What do you feel when the cord attached to your body and you hit in that velocity? You'll feel that the cord actually pulling you. So the arrow is pointing inside. Okay, you look at that body. You look at that body. Then W point in and D out. Okay, so you have this free body diagram. You use conservation of angular momentum. Okay, because conservation always linked with energy and momentum. Okay, the rest you read. You write H1 equal to H2. In this case, O is origin, O. So if from O here, actually I left out the O lah. I should draw O here at the origin here. Right? So H1 is momentum, angular momentum at this position. H2 is angular momentum at this position. So again, moment of momentum is distance multiplied by the momentum. The distance is R1. After R2, this is R2. R2 and V dash means after. After we did this one. Okay, you put in the R there. This D2, we're not sure what is the direction of V2, but we know that the resultant we can split in R direction and the tangent direction. So you substitute all the known value, the R1 you know, M you know, velocity you know, R2 you know is stretch 0.2, so the final length is 0.7. Mass remain, you don't know the velocity, so only one unknown. Rearrange, place calculator. So you get 1.07 meter per second after 5 seconds there. Okay, so you can solve using conservation of energy also. So what happens if you use conservation of energy? So kinetic plus potential. Remember potential, you have two things. One is gravitational. You have spring. So you have two. Gravitational means mgh. That is different from the datum. Above datum positive potential, below datum is negative potential. Another one is spring. There are two mechanisms that link to the potential, weight W and the spring. So in this case, you have the spring. Spring energy is kx squared. I remember that. Remember that. So mv squared is kinetic. Half kx squared is spring energy. So before, after, m you know, v you know, k you know, x you know, x1 you know, unstretched 0. So here after m you know, vd2 you don't know, k you know, kx2 you know, kx2 is 0.2. So you substitute, you can still solve using conservation of energy. You arrive at the same answer. Not same answer, but you arrive at the vector of d. Okay. Then you have this Pythagorean theorem. Okay. There's a triangular here, triangular here. So D2 is a resultant. So resultant equal to this V dash 1 and or V prime plus V double prime. We rearrange the equation. You square it, means you square this one equal to this one. Substitute, you get V dash 2. So I hope you can see the difference between conservation of energy equation and this one, principle of angular impulse and momentum. So if you use principle of angle, impulse, and momentum, the V that you find is on the tangent, not tangent, is on the tangent direction. But if you use conservation of energy, the V that you find is the final resultant velocity direction. Means you don't know, you actually look at the tangent or normal direction if you use conservation of energy. You only look at the final magnitude of that resultant. Yeah. So this is the difference between principle of impulse and momentum and conservation of energy. So these are different. So you know. We won't go deep. We won't go into this one in float system, because you are mechanical and civil. If you take aerospace or aeronautics engineering, then this one is important. But you have all the info here. Just go home and read for your extra knowledge lah. So maybe you'll see this one in the hydraulic or in the fluid mechanics module. You still use the same principle. Okay, any question? No, we conclude chapter 4. Next lecture, we look at chapter 5 already. Okay. Okay, sign your attendance. Sign your attendance.